today's tutorial will cover these, I guess, some applications of the gradient of a function. Okay, so what can you do with grad f? Now, one application is to use the gradient to form, normal and tangent lines and tangent planes. And we'll also be looking at tangent planes and differentials. Now, I guess here we really mean we're sort of estimating complicated values by using a tangent plane as an approximation. So let's look at the problems. And I know the font's really small here, so you might have to look in on your own notes or something. But in 68 Part A, you're given some sort of curve, and you're asked to find the equation of a normal line and the tangent line for each of the following curves at the point indicated. So let's have a look. So consider the curve given by this, and say the point P, which is just 1, 1. Do you want to just turn that light off and see if it actually shows up a bit better? Not really. I'll just keep the light off for now. What's that? If you can bring it down, that'd be good. Okay, no worries, thank you. That actually makes a bit of a difference. Okay, so we're asked to calculate the equation of the normal line and the equation of the tangent line to this curve at this point. So, any ideas? Gradient, right? The gradient will help us out. So let f be defined by the right-hand side of this. Grad f, evaluated at the point of interest, it produces a normal vector to the curve. Okay, so we're working in the plane, so we're talking about normal vectors to curves. So let's go through and calculate it and see what we can do with it. So we're going to get something like 2x minus y minus x plus 2y, and we want to evaluate that at our point P. So if I plug in those, I should get 1, 1. Okay, well, let's see what we can do with it. Oh, I guess let's call this part I. So we want to calculate the equation for the normal line. So the line that's normal to this curve at this point. So okay. I guess we can just go OP. So the vector OP plus T times the gradient of F at P. Yeah, that's nothing. Okay. So, question? No? Okay. So this is the vector form, the vector parametric form. Remember, t's the parameter here, or I guess the variable. Now, if you rearrange this, so x, if you want to sort of write it in this form. And then, eliminate t, you'll get the following. Okay, it actually simplifies quite nicely. So that's the first part. So you can hopefully see that having a normal vector to either a curve or a surface can lead to really good things. Okay, we can get equations of normal lines, we can get equations of tangent planes, and all sorts of things. Part 2 is slightly trickier. What they want you to do is calculate the equation of the tangent line to this curve at this point using the gradient. Let's do it using the gradient. Okay? So this is at P. Yeah, or through P, I guess. Okay, anyone done part B? Part I? Anyone? Yeah, how did you do it? Okay, yeah, not bad. Let's see if we can, I guess. Can
you use the dot product and set it to 0?
Yeah, you can do that as well. Yeah. So there's a few ways you can do it. So let me just sort of use this vector type approach, and you can, we should get the same answers. Okay. So let's call this, I don't know, R1 and R2. Okay, so what do you need for the equation of a line? You need a point on the line and its position vector. Well, that'll be that. Plus t times some vector v, where this vector v is a vector that's parallel to the line. Now, what do we notice? If that's our curve and that's our point, we want the equation of the tangent line. What do you notice about a vector that's parallel to this line L and this gradient vector? Well, the angle's pi on 2, right? They're normal to each other. So the dot product is going to be 0. So the only thing stopping us from finishing this problem is finding this vector v that is parallel to our tangent line. Okay, so let's obtain v from the following. Okay, the dot product has to be equal to 0. So let's say v, say v1, v2. Then take the dot product of this v1, v2 with v1. So let's choose, say, v1 to be 1. That means v2's got to be -1. So then put this back into here. So OP is just 1, 1. V is just 1 minus 1. So 69C. Find the equation. So I'm not going to sketch it. I'm just going to actually find the equation of the tangent plane. Again, this is another useful I guess, application of the gradient. So 69 has the following. So this time we're working in three-dimensional space, and we've got some sort of surface associated with this equation. And I've got a point of interest. Okay. So if I let this left-hand side just be f, then what I'm going to do is look at the gradient of f, produce a normal vector, and then look at the equation of the tangent plane. So the important information here is that we recognise that grad f, evaluated at our point of interest, gives a vector normal to the surface f equals 0. Oh, sorry, f equals 2. Okay. All right, so let's go through and calculate the gradients. So in this case, it's going to be the following. And so at our point, it's going to be 2x minus yz minus xz and minus xy plus, plus 3z squared, all of this. So now if we sub these values in, according to my calcs, we'll get the following vector. Okay, big deal. We've got the equation, we've got the a normal vector. So what we want to do is calculate the equation for the tangent plane. Now you can get the equation for the tangent plane in a few different ways, but one way is to have a normal vector to the plane and a vector in the plane. You just dot them together, set them equal to 0. So for our tangent plane equation, we use something like this. We want a normal vector to the plane, and we want some other vector in the plane. So x, y, z is just some arbitrary point on the plane. And we know the dot product's got to be 0. So here, our normal vector is just the gradient vector. So we're going to form the following. Okay, so let's look at this vector here. It's going to be x minus 1, y minus 2, and z plus 1 equals 0. So now I can just expand that out using the dot product. This is our equation of our tangent plane. Now you can simplify that if you want to. I'm not going to. Okay, I'm not going to draw the equation of the tangent plane. If you wanted to go one step further, I've just got it written down here. You can, but you don't have to. If you're in the exam, this is fine, I believe. This is fine. I certainly wouldn't penalise you for not simplifying that because it's easier to mark when it's in that form. Any questions so far? A couple of, standard applications. Okay, sorry? 74 is a slight change of pace. We're asked to use differentials to find an approximate value for this nasty looking square root. Anyone done it? Anyone done 74? Anyone? Okay. 74 is a good one to do because it's not, it's sort of a little bit dissimilar. Let's say we want to approximate this value. What do we know that this value should be? It's 1.02 cubed plus 1.97 squared. What do you think it should kind of be? Yeah, well 1.02 is almost equal to 1 and 1.97 is almost equal to 2. So if you replace those with 1 and 2, you're going to get square root of 9. So the value here should be around about 3. Okay, so that's a very crude starting point. But we can do better. We can do better than that. Okay, so what we're going to do is use the tangent plane, approximate this to sort of a first degree type approximation. So how do we do that? All right. So instead of this sort of value here, I'm going to introduce a new function based on the structure of this setup. And we wish to approximate this following value. Okay? Okay, so if you look in lectures, we've got, using the tangent plane and the increment in f, we can come up with some sort of approximation. So let me just refresh your memories here. Uh, 1 and 2, yep. Now, you can see that these two values are just x naught plus delta x and y naught plus delta y. Okay, so so what we're doing here is these are sort of small changes from these simple values. Okay, so we're going to use the simplicity of these values to approximate the value of f at these sort of nasty values. So we're going to use the following. Now, in this sort of notation, I'm going to have the following. Oops. Yes. And from lectures, using the tangent plane approximation, I know that this is approximately equal to the following. Okay? So over here, this is like the equation for a tangent plane, and over here, this is some sort of value on a surface. Okay, note the approximately equal to sign. So let's work out these things, and in particular, this is going to be pretty easy to evaluate because we're working with simple inputs. Okay, so f of 1, 2 is just going to be root 9. Let's differentiate and sub in 1, 2. So let's partially differentiate this with respect to x. And I want to evaluate that at 1, 2. And then multiply everything by this delta x, which is 0.02, plus this bit. So just differentiate again. I guess technically these should be like, oh, no, that's all right. That's okay. I can leave them as x's and y's. Yep. X cubed plus y cubed, all evaluated at our simpler point. And this bit is multiplied by delta y, which is minus 0.03. Okay. So now all we really have to do is substitute these things in, and we'll get some sort of value, some sort of approximation. So this is going to be 3. If I sub in x equals 1, y equals 2, according to my calcs, I'll get something like this. And I'm multiplying it all by 0.02. If I sub in up here, I'll get something like 12 onto root 9. Again, multiplying by minus 0.03. And then if you simplify these values, you should get this.